But thanks again to this month's Marine and Antarctic Seminar Series event. This time we're looking at, well, they're always topical topics, aren't they, but marine renewable energies. And the rationale for choosing this subject is that we know that it's going to be an increasing part of our energy procurement landscape and also part of our marine spatial planning and ecosystem-based approaches to what we do with Australia's marine estate. We're also aware, of course, all of us are, of how much more developed this sector is in the Northern Hemisphere. So we are at a point in time where we have, if you like, not necessarily off-the-shelf products, but this concept of a sector that could emerge significantly in the Southern Hemisphere with a lot of the insights from the failures and successes from the Northern Hemisphere that we can draw on. So in usual fashion, we've taken a really sort of multidisciplinary approach to this. We've drawn on Mark Hemmer from the CSIRO, who's got essentially leads a large part of that institution's research into marine renewable energies and is an oceanographer by trade. And we've also asked Dr. Jessica Walker from the AMC to come in to talk about some of the engineering challenges, and in particular she'll be looking at turbines and biofouling. And then we've asked Dr. Karen Alexander, who is actually an IMAS local, to talk to us, though, about some work she did previous to coming to IMAS about that Northern Hemisphere, about the introduction or development of the marine renewable sector in Scotland and the conflicts it had with other sectors and the broader implications for governance. So the reason we've tackled it in this way is to ask, well, given we all know normatively that we want this sector, we want marine renewable energies to be part of the energy mix, what are we looking at to enable that to happen? What are the kind of technical challenges but political challenges that we're facing too? And do we have enough knowledge in the first instance of the fundamental physical oceanography too that we need to have to drive this sector? So hence the people we've invited to talk. Mark, luckily, is going to be able to give us a bit of an overview of what we're even talking about when we talk about marine renewable energies in an Australian context. So I'm going to hand over to Mark, and then we'll save questions probably till the end, if that's okay, unless someone's got a major clarification, and then we'll have our three speakers up at the end to talk through some of the tensions and interactions between their three topics. And just a reminder again, this is a ResCom initiative, I can see Katrina looking at me, that's supported by IMAS Research Committee, but more than saying that, we really invite ideas and topics. So really you've just got to come to us with an idea and we can do the legwork and find the people and order the food and the venue. So come to us with these topics because I think it's an important part of our research practice, not only to deliver these kind of more research-oriented presentations, but to actually understand our issues as topical issues as from a public interest point of view too. All right, thanks everyone. So I'm going to introduce over to Mark now.
Thanks. Do I need the microphone?
Yes.
Yep.
Yeah, don't do it right here.
No. That's on? Yep. Okay, thanks. So firstly, I gave a seminar on this topic about a month ago at CSIRO, and this is just a succinct version of that. So apologies if there was anyone in that audience. There's nothing new in this. So I was very much talking then about ocean renewable energy, whether it is an opportunity as it's kind of pitched in amongst the marine community, or whether it's a distraction, which is kind of what the energy sector looks at it as. So this is just some of our work looking at one of the wave energy converters over off the Perth coast, Carnegie Clean Energy Limited. So I'll mention that a bit later. So ocean renewable energy is being pitched at the moment as an emerging technology, and so the first point I wanted to make is that it's not really emerging. This picture is taken from outside the Sorrento Museum on the Mornington Peninsula in Victoria, and this ball is the electric ball. That was part of Australia's first wave energy converter deployed in about 1909. It was connected to a series of pulleys and levers and such like that drove an electricity generator on shore, and it said that it powered a light bulb for some time. I recently learnt that the inventor of this, Alfred Robshaw, actually died within about 6 months of this project going in. So whether wave energy might have had a better future if he hadn't died so soon after, who knows? As it was left to his 16-year-old son and his mate to dismantle it and dump it in the family paddock. So I thought it was worth talking about the technologies that we're talking about, just an introduction. I'm sure Jess will talk more about these, but these are in kind of order of increasing maturity, if you like. So wave energy converters, there's a whole range of wonderful technologies that harvest the kinetic wave energy and convert that to electrical energy. And that can be done by different submerged buoys, oscillating flaps that sit on the seabed, oscillating water columns that are like a blowhole system that drive an air turbine. This is a flexible membrane that sits on the seabed where the wave pressure differential drives an air turbine within this chamber, and then other buoy and snake-like systems. There's a whole range of different technologies that haven't converged on a standard approach. If you look at the tidal energy converters, we talk about tidal energy being tidal stream, and where they're harvesting the energy from tidal currents or tidal range, like tidal barrage systems or lagoon systems, which operate similar to a hydroelectricity plant, if you like, where water flows out through a turbine. These tidal streams are generally where the emerging technology is. You can see that they're a bit more mature, and all these devices are tending to converge on a common format, if you like, in that they're horizontal axis turbines with just varying number of blades and such like. There are some other technologies like this underwater kite that harvests energy as well. And then there's offshore wind, which is now a commercially viable technology. We see the widespread deployment of this in European seas, particularly mostly platforms fixed to the seabed. But now we're seeing emergence of floating platforms. We haven't seen developments of offshore wind in Australia. There's a significant project proposed for the moment. But one of the issues with offshore wind in Australia is there's very few sites where you could have these fixed platforms. Now that we're seeing these offshore floating platforms, I suspect that we may see more projects being proposed for Australia. And then there's a whole range of other technologies which are less mature again, like ocean thermal, ocean current, salinity gradient and such like, which I won't go into. Why might you consider ocean renewables in Australia? So I guess I approach this from the climate perspective, in that over the next few years, if you think about the COP21 agreements, we need to see significant reductions in our emissions over the next decade or two. There's talk about reducing emissions by 65% over the next by 2030. So very rapid reductions rapid changes in technologies required. And I argue that challenge is significant enough that all technologies that are able to contribute to that should be on the table at least. So that's the main driver from my perspective. Solar and wind is where renewables are at the moment, and they can deliver to our current policy needs, whether that be the renewable energy target or the national energy guarantee. But when you get to scenarios where you have high penetration renewable energy, so 50, 60, 70, 80% renewable energy, then you need to deal with the consistency issues associated with solar energy, and they fluctuate, and also wind. So that can be offset by storage, whether that be battery storage like we've seen in South Australia with Elon Musk's battery, or pumped hydro storage, which is where some of the conversations at in Tasmania and New South Wales, or alternative means of generation, whether it be bioenergy, geothermal, distributed energy systems that contribute and even out below. To argue for ocean renewables, we've arguably got the world's largest ocean renewable resource. In terms of waves, I can say that confidently, and in terms of tidal, I can put it in the context that the Northwest Shelf occupies about a third of the global tidal energy resource. So there's significant resources in that respect. And you can argue that the wave energy resource, at least, is close to demand. 85% of Australia's population lives within 50 kilometres of the coast, most of that being on the eastern coast or the southern coast, both of which have fairly attractive wave resources. And then there's the arguments around the socio-economics about building a blue economy, supporting a transition from a declining offshore energy industry into this, and such like around that. What's the status of Australia's ocean renewable energy at the moment? As far as tidal, we can say there's not really been any projects. There's been a couple of very small demonstration projects, but that's about all. So it's mostly been in waves. And this map shows, well, firstly, the blue is where our wave resources are. And then the arrowed labels are where different demonstration projects are being carried out by different companies around the country. So these vary by their technology readiness level, which is an indicator of how mature the technology is, higher being higher maturity. You can see there's a number of different companies. There's probably about 8 or 9 different companies that have tested their devices at different scales. But if you look across these now, there's really only 2 active projects, and I think that really reflects the ephemeral nature of these companies. There's small companies trying to do large infrastructure projects, and they might it's difficult to survive. So the 2 most active projects really are the Albany Wave Energy Project and Waveswell Energy, who are developing a project on King Island at the moment. The rest are really well not proceeding at all. The only, I guess, Bombora has moved across to Wales as the only kind of export of intellect. In terms of the public purse that's gone towards Wave Energy Project, ARENA's been the major investor towards wave energy projects of about what I say is non-trivial seed funding of about 53 million Australian dollars across 10 projects. ARENA's, I think it's fair to say that ARENA's stopped funding marine energy projects, particularly wave projects. The last project they funded was probably 4 years ago. In the last year, they've shifted their priorities to be around grid stability and providing secure energy, so concentrating on grid infrastructure, innovation of solar PV, and renewable energy export, looking at hydrogen and export hydrogen fuel carriers and such like. So it's much more difficult to pitch ocean energy projects in under ARENA funding. And then the other major investor in Australian government circles has been the West Australian state government. So last year, I would say that wave energy had almost stalled entirely in Australia. The West Australian government promised $20 million towards the Albany Wave Energy Project through their Regional Development Fund, which is funding Carnegie Developments and University of West Australia Research Centre down there. At the time, all those previous projects were kind of taking off was about 5 years ago, and at the time we started this project around the Australian Wave Energy Atlas, which was really to build some pre-competitive, some knowledge base to support the growth of that industry. And the idea was trying to address 3 gaps that the industry was struggling with. One was understanding the resource. One was around the difficulty they had in terms of accessing other marine spatial information data, so marine protected areas, shipping lanes, oil and gas leases, all the other spatial constraints on where project developers might site a project, and then also the limited evidence base around assessing the impacts of wave energy extraction on the marine environment. And so out of that project, it finished about 6 or 12 months ago. We delivered the Wave Atlas and some guidelines around assessing impacts. This is what the Atlas looks like. Gives lots of information about resource of different layers, and also you can view that information alongside characteristics of the marine spatial domain. So here we've just shown the Commonwealth marine protected areas, and also information on the electricity infrastructure, so here being the electricity grid. But there's a whole suite of other information there that may or may not be of interest. But in terms of, I guess, what came out of that work is really a better assessment of the resource. And in the general conversation, you might hear of Australia's huge wave energy resources, and so I think it's worth putting that in context. So this dot represents the size of Australia's wave resource at 100 metres water depth, this being Australia's electricity demand. And so this is where the figure about Australia's huge resource comes from, is that we exceed our demand. But to put it in context of other renewable resources, our onshore wind resources and our onshore solar resources, and then also our coal reserves. And so I think that kind of puts into context, from a marine community, we say, oh, we're interested in marine renewables. If you're sitting without that marine perspective, then this is a fairly compelling argument as to why you might look at solar and storage and such like, which is where ARENA is sitting. Internationally, Australia's kind of unique in terms of the wave resource being larger than our demand. Most of the development of converters is going on in Europe, the US and China. You can see that they're different countries, obviously, but their electricity demand is much higher, larger than their resource, but they are spatially constrained, and so they're looking offshore to generate their power offshore because of their spatial constraints onshore. Some of the other work we do in terms of the size of the resource, obviously we've got a large resource, but it takes into account no other spatial constraints or such like. We're only interested in the resource that might be close to demand. So I've done some work around what resource is close to the electricity grid, and also you can't deploy these things anywhere, so we might issue other spatial constraints. So here, just playing around in marine protected areas. So that figure of over 2,000 terawatt hours per year quickly gets reduced just in terms of waves across as they propagate towards shore. So at 25 metres, it's already reduced to 1,860. And then by the time you take in these other spatial constraints, you're down to 30 terawatt hours per year. So it's a lot smaller resource than what we were originally pitching as. And then this is the work we've done around guidelines. So at the start of the talk, I showed a photo of instrumenting behind the wave energy converters off the Perth coast. And we've been measuring the signal of how waves are attenuated behind the device. This is the swell, when WECs are in place and when they're not, so this being control. The red and pink lines are the buoys directly downstream of the devices. You can see the swell waves, you see this decrease all the time, and that's just because the long swell waves are being attenuated because they interact with the bottom anyway, but the high frequency waves are attenuated by the presence of the WECs. So what we're interested in is generalising this to look more broadly at a larger array types and such like. The issue here, of course, is that, you know, if wave energy converters are deployed, they remove energy from the natural environment, and that might have ecological benthic habitat implications and such like. So that's essentially what this is focused around. So that's the Wave Energy Atlas project. That's now complete. We've now picked up a very similar study on the tidal energy resource. This is being led by the Maritime College with UQ and ourselves as partners. CSIRO leading two of the three components, the three-component project. So the first component is very much a national tidal energy resource assessment to work out where the best sites are for tidal energy around the country. Component two is just picking up two of those sites and doing a focused study, both field-based and numerical model-based on those two sites. And the third component, led by my colleagues at CSIRO Energy, looking at the technical and economic feasibility of tidal energy and how it will pitch into that broader energy perspective in Australia. This is just showing the early results from component one in terms of most of Australia's tidal resource sits up on the Northwest Shelf and Darwin Coast. There's little patches down between the Bass Strait Islands and Tasmania of interest locally. The other work we've done is around identifying priorities if ocean renewables is to advance in Australia. There's lots of words on this slide, so I won't go through them, but just break it up into four sectors around the priorities in the technical sector, in the policy and regulation, education, awareness and investment. That's a recent paper in Renewable Energy if anyone wants to look at that. So this is just moving through quite quickly. So why aren't we seeing wave energy being picked up or ocean renewable energy being picked up broadly? It comes down to the economics of the thing. At the moment, solar and wind coming in at about $100 per megawatt hour as a unit of energy. Waves more expensive, tidal's a little bit cheaper, around $500 to $900 per megawatt hour. So it's an economic decision. There is argument that as waves are at the prototype stage and they'll be expensive, and as you deploy more of them, the cost will decrease. But if you look at where the costs come from in a wave energy converter, a large chunk of it's down to operations and maintenance. I suspect everyone in the room knows it's expensive and difficult to operate in the marine environment, and so that component's going to be hard to shrink. There's been some work by some colleagues in Europe that have looked at how much work you need to do to reduce that cost. They argue that you need to deploy about 3 gigawatts of projects to meet $150 per megawatt hour goal to be cost competitive with other technologies. That would require about €1.5 billion investment to install that capacity. There's about 60% of that proposed at the moment. But given there's other technologies already operating at that price, you kind of ask yourself, where's the incentive to spend that investment to start with? And then there's the research challenges around the development of ocean renewable energy. There's the technology challenges, which is really a precursor if we're going to do this, is to make sure we have a technology that works. There's the resources, so this is where AMC's work is really focused. Resource assessment and forecasting is really where our work's focused at CSIRO, and understanding the resource. And then there's work around environmental effects that we've also flirted with, but I think there's room for growth, and perhaps Karen will touch on that. But they're the effects of energy extraction that I spoke about, and the impact they might have on benthic communities. There's questions around entanglement, electromagnetic effects associated with subsea cables, underwater noise, a whole range of other stuff in that. There's the socio-economic impacts. I guess I'll make the point that there was a study a few years ago, and I think kind of came up in Emily's introduction, that everyone wants ocean renewable energy. There's a study in the UK that said ocean renewable energy came in as the second favoured renewable energy source, only close behind solar. And so there's a lot of social capital there. These are a couple of projects that have happened in Australia that have failed, where these failed devices have sat in the public view for a long time. So that social capital is quickly eroded associated with that. And so I think there's some interesting research that can be done locally around the King Island projects with this type of work. Happy to chat. And then there's electrical engineering questions and ocean engineering questions and the regulatory legal affair type questions as well. The positive drivers for ocean renewal, the climate change I spoke about, the amount of effort going on internationally and the opportunity there is for Australia, the resource advantages, niche opportunities. I'd say that most project developers have really focused on the utility scale energy supply, but I think they've now realised that their market is in terms of these niche opportunities, displacing diesel, where they're cost competitive now, potential opportunities around exporting hydrogen, which I mentioned, and then co-locating these devices with other beneficial industries. So aquaculture is one that's being discussed around these parts now, but also desalination, coastal protection and such like. I've mentioned these couple of points around transition industry, and then there's plenty of research questions that are applicable to this community. The negative drivers, it's not a favourable domestic policy environment in Australia at the moment, and perhaps even internationally. There's economic challenges, which I spoke about, not being competitive. There's technological advantage in terms of these resource advantages, which is really why you would pitch ocean renewable. They're being overtaken by other technologies. And then I made the point that we need to make a rapid transition to these low emission technologies. Maybe this will not be competitive at the time of need, and that's that point there around relative immaturity. So just to summarise, the industry is tenuous. It may not be a viable future option. There's a difficult domestic funding and policy environment in Australia. There's a lot of effort going on internationally. Australia's profile is probably limited in that international landscape, but we do have some strength. And then there's a lot of research challenges that need to be overcome. So that's happy to hand over.
Thanks very much, Mark. Well, we're going to invite. Yes, thank you. Do you mind transferring that over to Jessica? We're going to invite Dr. Jessica Walker now, and interestingly, some of the technical challenges she'll be describing, I'm imagining apply to both the sort of bespoke industry development option as much as the large-scale one. So, Jessica's an engineer at the IMAS. There you are. And let's all pick up. Thank you, Jessica.
So is this microphone working? Yes. Okay. Alright, so I'm an engineer at the AMC, as Emily said. I'm going to be talking to you today a bit more about the engineering technological side of ocean renewable energy, specifically focusing on tidal turbines, which is my own area of research. I'd like to start off, this probably touches a lot on what Mark was saying about why we're actually interested in renewable energy. Global energy requirements are going to balloon in the next 15 years. And we're talking about up to 60% increases in global energy requirements. So we need a resource to get that additional energy, obviously. Australia obviously has the 20% renewable energy contribution by 2020. Obviously, renewable energy is really attractive in that we're not using up our fossil fuel resources, it's less polluting, and also can be carbon neutral or negative. Ocean renewables is a very, very small percentage of the current global energy makeup. So renewable energy as a whole is about 13% of the global energy. Sorry, is that not on? Okay. Thanks, Nicole. Yeah, I didn't think it was on. So ocean energy, as of 2008, so I need to update my graphic obviously, was only 0.002% of global energy. Renewables as a whole, it was about 13%, And when we're talking renewable energy, I'm talking biomass, solar, wind energy, hydropower, geothermal. And ocean is just a very small proportion of what we call renewable energy. So why haven't we developed ocean energy so much yet? It's a really, really harsh environment that we're proposing to put these devices into from an engineering perspective. The flows are really energetic, it can be, and also it's a very corrosive environment. Okay, we're talking about putting engineering structures into an environment that's going to try and corrode them as quickly as possible. So that's a real challenge in terms of the engineering side of things. However, as Mark said, Australia has a really a large ocean renewable energy resource that can be developed, and it's something that personally I would really like to see developed. So what are we talking about in terms of ocean renewable energy? We're talking about tides, tidal currents, non-tidal currents, waves, salinity gradient, and thermal gradient. So they're all different sources of ocean renewable energy that we have. And as Mark would have said, the actual energy in our oceans is currently larger than our current global energy needs. It's just a case of how we develop that and how close that is to the actual locations where we need the energy. So at AMC, we are focused on two areas in terms of technologies, and that's tidal currents, which is my area of research, and also waves. So one of the reasons why ocean renewable energy is quite attractive in terms, and talking particularly about tidal current energy, is that the energy flux density that you get out of tidal currents is actually a lot higher than you get, say, out of solar or wind. Tidal energy is really, really predictable. It comes from the gravitational pull of the moon, so we can predict this years in advance what that tidal energy is going to be. And it takes advantage of local high velocity flows. So we can extract it, say, from narrowed channels, from entrances to bays, where you have really high velocity flows. So in terms of the Australian tidal resource, we're talking about areas up here in the Northern Territory and northern parts of Western Australia. There's quite a significant tidal resource there. And in terms of locally, in the Eastern Bass Strait Islands, in the Banks Strait, there's actually a fairly significant tidal energy resource there. So these are some of the tidal energy technologies that are out there. We have ones that are fixed to the bottom, so they're gravity mounted to the seabed. There's a range of floating devices. There's different numbers of blades. Some of them rotate about the horizontal axis. That's the more mature technology. We also have what are called cross-flow turbines that may rotate about the vertical axis or other axes. They can be open, like all of these ones, or they can be in ducts like this device here. The thing that all of these devices have in common is that they're all extracting energy from the tidal current to generate electricity. So they're all rotating in some manner to generate electricity from those tidal currents. So what is AMC doing in tidal energy or marine renewable energy? We have quite a strong collaboration with Australian industries, both in wave and now in tidal. And we help these industries develop their devices through experimental and numerical work. So we're testing their devices in our facilities and also helping develop an understanding of what the resource is. So where is the wave energy, where is the tidal energy going to come from that we can place these devices? So I would like to now talk a bit about what's happening in tidal energy research at AMC. That's my field. So we focus in two main areas. One is tidal device research. So that's bridging the gap between the design calculations of these devices and what's actually going to happen if we deploy these turbines out in the field. So we do experimental testing as well as numerical modelling of these devices. The other side of our work is in resource characterization. So we need to know accurately what the resource is at each site that we're considering putting turbines in, so we can know how much power can be generated. So we have a team that works on resource characterization as well. So in terms of turbine modelling, we need to know how a turbine performance, so in terms of its power output and also the longevity of the device, how long can this thing survive in this really harsh environment for? In terms of waves, so how deep do we need to go before our devices are not going to be affected by the cyclic effect of those waves going past? So we already know that if the presence of waves causes big fluctuations in power output, and also it's going to have big fluctuations in terms of the loads on the blades of these devices. And so in terms of fatigue loading and how long these devices can actually survive for. In terms of biofouling, obviously we're putting them in the marine environment. Things are going to want to grow in them. How much is that going to affect the power output? How much is it going to affect how long they can survive for? Other aspects include the turbulence and the shear. So the facilities that we tend to test in our experimental models, they don't have turbulence and shear, but obviously the oceans do. So we need to know how turbulence and shear is going to affect the performance of these devices. We need to know how submergence depth is going to affect them, as well as the impact of test facility and scale. So we're testing scale models in different facilities around the world. Does it matter which test facility we test in? Is it going to give a difference to our results? So at AMC, we test both horizontal and vertical axis turbines. You can see down the bottom here, this is our 100-metre long towing tank that we do the testing on. And this is one of our turbine models that we have. So it's a two-bladed horizontal axis turbine. We have two. The bigger one's 800 mil diameter and the smaller one's 500 mil diameter. And that's based on some work I did as a postdoc in the US, and it's based on a US National Renewable Energy Lab design. We also do a fair bit of numerical turbine modelling, so that's using CFD, computational fluid dynamics models, and we're able to model them numerically, both horizontal and vertical axis turbines, and we validate those models using our experimental data. And this allows us to investigate a lot of additional information. We can look at, for example, real detail in terms of the loads on the blades, the turbulence structure in the wake of these devices, which is important if you're looking at putting a whole lot of these devices in a row or in an array in the oceans. The other side of the work that AMC does, and Mark talked a bit more about this, is in terms of resource characterization and the AUS10 project. So that project is really looking at mapping what Australia's tidal energy resource is, where are the tides in our country that can generate enough of a flow that we could put a device in there and generate some power. So it's a project funded by the Australian Renewable Energy Agency as well as industry. And one of the sites that they're looking at in detail is off the northeastern coast of Tasmania in this Flinders Island group. So the team's been out on Bluefin, one of our vessels, a couple of times, looking at mapping in detail the tidal resource at that location. And as Mark said, one of the other sides of that project is really doing a feasibility study, looking at the existing tidal technologies, so the existing turbines that they have, and looking at, well, how much power could they actually generate if we were to put them in one of these sites. The other part of my talk that I wanted to look at is turbines and biofilms, because I thought biofilms might be of particular interest to this audience, and that's what my own background is in. So this work is work I did a couple of years ago in the United States. We're interested in what happens to our turbines if they happen to get fouled by biofouling, so whether that's a slime or barnacles, or what happens to our turbines if the blades happen to get damaged by particles in the water or they get struck by something. How is that going to affect performance? So we did some modelling. The first blade you can see at the top here, we tried to model sort of a slime biofuel, using grease that we impregnated with diatomaceous earth. And the second model here was trying to model more of a calcareous type roughness, so barnacles, and we just put some contact cement on the blade and then tested them in the towing tank. So this is the prototype full-scale sort of size turbine that we're trying to model. It's called the C-Gen. It's in Northern Ireland. You can see it's got two rotors. There's one rotor here and one rotor here of two blades each. and they're 20-metre diameter. So our experimental model based roughly off this turbine just has one rotor, 0.8-metre diameter, and we tested that in a 116-metre long towing tank at the United States Naval Academy in Maryland in the US with a clean rotor, so nothing on the blades, with that slime on the blades and with that contact cement trying to mimic a roughness. And this is some of our results. So what we're looking at here is a power coefficient. So a power coefficient is basically the ratio of the amount of power the device can generate versus the amount of power that's actually available in that flow. On the bottom we have tip speed ratio. So tip speed ratio is the ratio of how fast the device is rotating versus the actual current that it's experiencing. So for a smooth blade, which is our circle data points, the peak is about 0.42. So we can extract 42% of the available power in the flow to generate electricity using that device with smooth blades. When we introduce our experimental slime, this is our first data point here. So you can see there is a significant reduction in power that we're able to produce. Unfortunately, what then happened in subsequent runs is that it all sheared off the blades and made an enormous mess in their towing tank, and then basically gave us the same results as the smooth case. But it did show that having something on the blades is going to cause quite a significant impact on the power production. And the final case that we looked at was our rough blade. So that's quite a solid kind of roughness that we put on the blade. And this is our results here. So you can see the peak is about 0.34 or 0.32, so 32% of the available power in the flow was able to be extracted using the device. And it's about a 20% drop in performance compared to the smooth blade case. So it kind of validates our theory that, well, yes, if they're going to get fouled up, if the blades get damaged, it is going to cause a significant impact on the power production. So some of the future work that I hope to do is looking in more depth at this issue. So how does blade roughness affect turbine performance? Can biofouling actually be sustained on these blades? They do rotate pretty quickly. It might be fast enough that the relative velocity of the blades is such that they can't actually grow on them in the first place. But it's a valid question. And we also want to get better at modelling these biofilms. So obviously that grease that we put on there, it came off in the tank, and we only got one good data point out of it. So there's going to probably be better materials that we can stick on these blades to model these biofilms. And I'm actually hoping that we'll be able to grow some real biofilms on them by popping the rotor out in the Tamar River and then towing it in our tow tank. So there's some acknowledgements of some of the companies that I've drawn some of the material from this presentation from, and thank you very much.
Thank you, Jessica. I'll now get Karen Alexander to come up to talk to us about a different type of challenge.
Thank you very much. Okay, can I just start by saying I am so excited to talk about renewable energy today. For any of you who have seen me talk before, it's normally on aquaculture, and renewable energy was actually my first research love. So I'm going to be talking a little bit about some of the work that I did in Scotland on my PhD, which actually had the same title as this talk. So thank you very much to the two previous speakers, Mark and Jessica, because they gave all the introductions on tidal and wave energy, and so I don't have to do any of that stuff, and I can just jump straight in. So I want to start by just saying that, as we all know, coastal areas are becoming increasingly densely populated. We're seeing more and more uses being made of these spaces, and that ranges from more traditional uses like fisheries and oil and gas, and types of recreation, be it sea kayaking or angling. And we're seeing new uses such as aquaculture and now renewable energy coming in. And this leads us to a huge problem, really, because we're going to start to run out of space soon for different uses of the marine environment. But what this means is it means that we end up seeing quite a lot of conflict in the marine space between the different people that are using these areas. So, a long time ago, about 10 years ago anyway, in a very faraway place in Scotland, our fantastic First Minister at the time, Alex Salmond, decided that he wanted to have a renewable energy target of 100%. So all of Scotland's electricity supply was to be provided by renewable energy by 2020. As I'm sure you'll appreciate, that's a pretty ambitious target, especially in a place like Scotland, where we don't have the amazing solar resources that you can see in Australia. However, Mark mentioned earlier on that Australia has one of the biggest offshore, or the biggest offshore renewable energy resource in the world. Scotland had the biggest, or has the biggest one in Europe. So we were pretty well placed to really start looking into wave and tidal energy resources. So we had an estimated wave resource of 14 gigawatts and an estimated tidal resource of 7.5 gigawatts. And to try and achieve this renewable energy target, we had quite a lot of onshore wind already. We were looking at offshore wind. We have quite a few developments, particularly in the east coast of England, looking at collecting offshore wind energy. But our First Minister actually put out a competition to try and really push forward in this marine renewable resource, so the wave and tidal energy resource. And this competition was called the Saltire Prize. And what it was a £10 million prize to the first company that was able to generate a rather substantial amount of electricity. I think it was something like 100 gigawatts over a year period. So the first company that was able to do that, either through tidal energy or through wave energy, would get this £10 million prize. So as you can imagine, that's $20 million. That's a substantial amount of money for one company to obtain. So we saw quite a lot of competition. And to make it a little bit easier, the government actually laid out, in a sort of marine spatial planning format, a bunch of areas that could be used based on the wave and tidal resource. So they actually made the seabed available to the developers in specific locations. So these are the areas that are green, that was the wave energy resource, and orange, which are the tidal energy resources. And so the developers could actually apply for licenses to undertake pilot programs and then commercial programs in these areas. So this is what my PhD looked at. I was particularly interested in how conflict would happen in these areas, what the different uses were in these particular sites, looking very much at the government marine spatial planning process to some extent, and whether they even considered some of the restrictions, spatial restrictions around these areas. So I took one particular site. I should point out that I, at the time, was working around about here in a place called Oban, which is pretty much where I was brought up. I was very lucky and got to do my PhD very close to home. And so I picked a site that was quite close by in an area called the Mull of Kintyre Peninsula, and this was set aside by the government as a tidal energy location, so a potential site for a developer to put in tidal turbines. And so I started off by looking at some of the different uses that were already going on in this area. And some of the things that we came out with were commercial fishing, commercial shipping. There's a huge IMO shipping lane that runs between Ireland and Scotland. There was some diving in the area. I should point out, this is me diving. This is what Scotland looks like when you dive. It's actually quite pretty, even though you can't really see further than about a metre away. There's quite a lot of recreational sailing that happens. A lot of sailors come from Glasgow here and they sail around the peninsula up the west coast of Scotland. We had quite a lot of wildlife tours and also wildlife itself. another consideration when you're actually looking at putting these devices in, particularly when there are considerations such as strikes and things like that that might affect your devices. And what we did was we actually started creating, I worked with some very clever people from Amsterdam, by the way. I should point out that I'm not the GIS miracle worker that my colleagues were, but we did some really cool work with the local community. So we started off by mapping what data we already had in terms of how the area was used. And then we took these maps and held workshops with the local community and said to them, look, is this data correct? Do we actually know how you're using the area? And how is it going to be affected if we actually look at putting tidal turbines into this area? If a developer takes this site on, because at the time there wasn't anybody that had taken that site on, so we were very much in a hypothetical situation. And we asked them if the data was correct and then how this would affect them. And we looked to see if we could actually establish areas that the developers could put the turbines in within this location that wouldn't have an impact in all the other users of the area. So it was a very marine spatial planning kind of exercise. And in it, we combined geographical information systems, GIS. We combined that with multi-criteria analysis. So we took into consideration things like resource, distance to the closest grid access, distance to port, a lot of the different considerations that would come in for the developers, but then also a lot of the considerations that come in for the people using the area. And we used this awesome thing called a touch table. So I don't know if anybody's heard of what a touch table is, but it's basically like a gigantic iPad. It's about 1 meter by 1 meter, or in fact, even a little bit bigger than 1 meter by 1 meter. And you can have lots of people using it at once. So it's a really cool device. I'm desperate to try and get one for IMAS, because I think we could use it in all sorts of different ways. But we had a really old school one. So whereas now with iPads, you can just like touch them and use them and they're great, our touch table was totally old school. It was like this big screen that lay flat on a table. It had a projection lamp above it. It had these little mats that you had to sit on that were attached by electric cables. And as the person running the workshop, the only way I could use the touch table was to put my hand on somebody that was electrically connected to it to be able to use it. So it was properly old school, but some of the more up-to-date touch tables which I've worked on more recently are just like giant iPads. But what it allowed the people in the workshops to do, so these community members, they were able to draw on the maps, they were able to move things around, they were able to identify in terms of ranking what areas were most important for them. So this map here shows the commercial fishing map. This was the one we started off with based on data that was available from the government. This was the one that the fishermen in the area drew on and said, well, no, this is not entirely correct. This is not how we use the area. And then we were able to change it and rank it based on their feedback. So we did that for all of the maps, for all of the different stakeholders, had maps for each of the different stakeholders. And then my very clever colleagues from the Netherlands were able to create, using these maps, a map that showed what area was important to the different stakeholder groups, so that they could look at each cell in the area and see whether it was important or not important to them, just at an immediate glance. So for example, in this square here, it has a blue S. That means that it was an area that wasn't used by any of the sort of what we classed as more social users, so that would be recreational uses mostly. Whereas in this cell here, you can see that there's a red C, and that means it was an area that was used by commercial users. So from that, they were able to see what areas were important or not important to them. And then we asked them to actually locate different sized installations within that grid, based on them coming to a compromise as to whether it was an area that was important to them or not. So this was a really cool process, but what was actually more interesting was that at the same time as they were messing around with the touch table and drawing things and moving things, they were also discussing what was going on, and that was the really interesting and important part of this whole process, because we discovered quite a few things. First of all, we discovered that commercial fishermen in this particular location were the people that were most likely to be impacted by this development. So that was a problem, and that was what the rest of my PhD ended up looking at moving forward. We found out that there were quite a few concerns and we see this with every new use of the ocean, there were quite a few concerns over the issue of precedence. So a lot of the stakeholders were saying, well, hang on a minute. You're taking this very much from a point of view of you're going to put in a tidal energy development. So therefore, they're taking precedence over the uses that we're already doing already. Okay? So this was a huge problem, and it's a really important issue for public policy moving forward, especially with development, for example, of aquaculture, as we see in Tasmania. There needs to be discussions around if we want aquaculture, if we want renewable energy, is it going to take precedence over other uses of the marine environment? So that was a really interesting concept. Another one that came up in the discussions was the issue of liability. So if fishermen do fish near renewable energy devices, who's liable if something goes wrong? Who's liable if a turbine falls apart and hits a whale and kills it? You know, there's a lot of issues around this. So we started to see some of these really interesting conversations coming out. And I think that's a really important thing for renewable energy moving forward, is we need to think about some of these issues before we automatically say, do you know what, we want renewable energy, we can get the engine, we can get the devices sorted out, we've got the resource. There needs to be this social discussion, and especially, we mentioned earlier on a little bit about social license. If you're going to get social license for any new industry, and this is where my particular interest lies, is around the issue of social license, there really needs to be some sort of conversation held with the people that are going to be affected. So I just want to finish off by saying, if we're going to look at Tasmania, if we're going to look at renewable energy in Tasmania, what are the different uses that are being used here? Or what are the different ways in which the marine space is being used here? We've got commercial fishermen, we've got recreational sailing, angling, we've got aquaculture becoming more prominent. We've got, I couldn't find a symbol for Aboriginal heritage, but this comes into it as well. And we've got people that are walking around the coast. We've got lots of people that are using these areas in different ways. And so really, if we're looking at renewables in Tasmania, what do all of these different uses mean? For example, up in this area where we've got a resource for tidal energy, you know, what does it mean for all of these users? And how are we going to move forward and take their considerations into account, or are we at all? Or are the government just going to steamroller through and say we're putting them in and that's it, tough? You know, these are some of the sorts of discussions that we really need to be having moving forward. And I'd just like to finish by saying that, believe it or not, the work that I did around the Mull of Kintyre area, a developer went in there after I'd done the study, actually asked me for all the data from my study and used it to make their decisions on where to put tidal energy turbines. So it can, this sort of information does actually get picked up and used. And that's it. Thank you.